I decided to study electrical engineering while I was still doing my previous degree, which was in music. I was sitting in this class called Electronic Music Studio, and for some of my projects in that class, I had studied a little bit about speech signal processing, which in turn got me into just reading about like all these DSP papers, digital signal processing papers, and I noticed that the people that had written those papers, well, they had studied electrical engineering. So I was like, well, I guess I'm gonna have to study electrical engineering too. So here I am. And so when I saw the description for this class, and it was like, oh, we're going to learn about Fourier series and the Fourier transform, I was really excited. So I just kind of wanted to share some of why I was so excited and what got me into this. So yes, this video is going to talk about how Fourier series are used in music and how the Fourier transform is useful for applications like speech synthesis and speech recognition.
So this is white noise, which means that all frequencies are present in the sound. As you can see on our sonogram here, pretty much the entire frequency spectrum is lit up, and our spectrogram, see, like the entire frequency range is pretty much covered. Yeah. So if we do, like for instance, if we do a low-pass filter, we can only allow low frequencies, then you get something like this. So here's all of them, and here's only the low ones. So when I do that, if you watch the sonogram, you can see that it's you can see that the high frequencies up here, well, they are not present anymore because we filtered them out. So that's also why they're a little low down here on the right-hand side of the spectrogram. The sonogram and the waveform view here, they show time. So they're like scrolling with time. So like this is what's happening now on the right-hand side, and this is what happened a while back on the left-hand side. And the oscilloscope is the same thing as the waveform view, it's just really zoomed in. So you can see things like wavelength, which we're going to talk about in a second, on the oscilloscope, but you can't really see it on the waveform. Yeah, so the spectrogram shows the instantaneous frequency spectrum. So like at any given point in time, this is what's going on. So let's do a high-pass filter and see what happens. So this is all frequencies. And I'm filtering out the low ones. They're going away. Bye. If I do a bandpass filter, I can, instead of doing like only the high ones or only the low ones, I am excluding high ones and low ones to a certain range, and I'm only allowing a certain band to pass through, which is why it's called the bandpass filter. Kind of neat.
So what if there was only one frequency in the sound? What would that sound like? Well, it would sound like a sine wave, like this one.
Hello, sine wave.
So as you can see, there's only one frequency present in the sound, because on the sonogram there, we only have one line, and on the spectrogram, we have one peak. This is a good time probably
to talk about wavelength. So on the oscilloscope here, we can see that we have a lovely periodic sound. So if I make the amplitude smaller, you can see that the wave height decreases. Single lig. And the color here gets more intense, and you get higher up on the y-axis, which shows amplitude. What happens if we change the frequency? If I make it lower, watch the oscilloscope. frequency, the wavelength gets longer, the wave gets slower, and then as I increase the frequency, the wave gets faster, and the wavelength decreases. So right now we're at 140 cycles per second. Okay, now watch the sonogram and spectrogram now. As I change the frequency, you can see that one peak. You can see it moving. He's making his way across right now. Oh, look at him go. Look at him go. Look at him go. Okay.
But as you probably have guessed by now,
Most sounds have more than one frequency, because most sounds are not a sine wave. Well, let's take a look at a square wave. There's more than one frequency, because we have, on the spectrogram, look at that. We've got 1, 2, 3, 4, 5 peaks shown.
and on the sonogram, we also have more than one line.
If we look at you can see that the wave shape is definitely different from a sine wave. So if you look at that, it looks squarey, because it's a square wave.
You can tell that it's
Still pretty regular, like it's periodic. It repeats. And the reason why it's periodic, the reason why it repeats, is because all of these... So you see how the peaks are evenly spaced? So like the peaks on the spectrogram and the lines on the sonogram, they're evenly spaced. So the lowest peak, or the lowest line, that's the fundamental frequency, and then the ones above it are called the harmonics.
and the harmonics are all multiples of the fundamental frequency.
Well, let's look at this oscillator bank. So each of these sliders corresponds to the amplitude of a sine wave. So this is the amplitude of one sine wave. This is the amplitude of another sine wave. This is the amplitude of a different one. And all these sine waves have different frequencies. So like, let's make that better number. So if we do 1. So 1, 2, 3, 4, 5. You get it. Like 2. 2, 4, 6, 8.
Let's do one we can hear. Let's make the C3, and let's listen to that. So I'm going to add one frequency, so we have one sine wave playing. It's called additive synthesis, by the way. Add frequency components.
Yeah, so if you like pop music, anything with synthesizers, there might be some additive synthesis in there. Now let's add an octave above. Let's double the frequency. So I'm basically just adding those two sine waves together. And you know that thing that we learned about when you add cosine and sine waves together, the whole Fourier series thing? Yeah, this is basically that. So when I set the amplitude of these waves, I'm basically setting the coefficient for that component. I mean, with the Fourier series, the frequency of each of the sine and cosine thingies is a multiple of the fundamental frequency. So yeah, these are all multiples of the fundamental frequency. This is our A1, or A2, A3, A4, A5, A6. I'm setting them to whatever this value is. Let's call it 1. I don't actually know. Yay!
Let's listen to some other combinations of harmonics. So here is every other one, and it's the odd-numbered harmonics. Wait, no, it's the even-numbered harmonics. And as I move this, you can see them move with so the fundamental frequency, the lowest one, is moving up, and since these other ones are all multiples of the fundamental frequency, as I increase the fundamental frequency, they get more spaced out, which is pretty interesting. So how about this one? So this one I skipped every 3. Has more of a thin quality to it. This one I think sounds a little bit like an oboe or a bassoon, some kind of reeded instrument. So the way that this all relates to speech is through basically the source filter model. According to the source filter model, like all the speech sounds that we make are basically a source, so like your vocal cords going and then a filter, which is your vocal tracts, and you manipulate this filter by moving your tongue and opening and closing your nasal cavity, also by rounding and unrounding your lips. So the higher or lower your tongue is, how far forward it is in your mouth, all of those things play into what sound you're making. Or if you've ever held your nose while talking and then been like,
Oh, why do I sound really weird?
it's because you changed the filter. So if we use, let's model the source, let's model our vocal cords using the sine wave bank. Alright, looks good. And now let's put it through a filter. So just like with the low pass filter, and just like with the noise, we can allow only low frequencies. We can allow all frequencies. We can allow all frequencies. We can only allow high frequencies. Or we can allow a specific band. With speech recognition and synthesis, pretty much vowel sounds are characterized by 2 formats. You can also do a third format, but the format 1 and 2 are pretty much the bare minimum for recognizing vowels. And what these formats are basically characteristic peaks in the frequency spectrum. So like we have this bandpass filter here. That's 1 peak, right? You can see it's producing 1 peak on the spectrogram. And so we want to make 2 peaks, one for each format. So we're going to need basically 2 bandpass filters in combination. So here's a E sound. E. Okay, and then we're about to hear I. So it's going to go E. Yeah, okay. And that's an A. Here's a E. Very lovely. So, yeah, that's pretty cool. That's pretty much everything I wanted to talk about. So, thanks for tuning in. I don't know if there will be a next time.